So if you're watching this video, that means you've completed the assignments on Nexus that are associated with the lab, and hopefully you got results that are, consistent with what we expect from physics. What are those results? Well, you should have seen that when you place small objects in the path of a laser beam, you get not a single shadow in the beam dividing it into two pieces, but you get a series of many bright and dark spots. This is exactly what Thomas Young reported seeing all the way back in 1804 when he was doing these experiments originally. If we look at his description, he says, besides the fringes of colors on either side of the shadow itself was divided by similar parallel fringes of smaller dimensions, differing in number, according to the distance at which the shadow was observed, but leaving the middle of the shadow always white. That is sort of a long-winded 1804 kind of way of saying he saw a bunch of bright and dark spots. Now, he was doing this with white light from the sun, in which case the fringes that he saw were lots of different colors. And I will put a link to a video on Nexus that shows you what the results of something very much like Young's original experiment actually look like. That's a lot harder to do, though. The lasers provide a nice single color, gives you a much cleaner image that hopefully you were able to get some good pictures of and really see what was going on. Why does this happen? Well, Young says that in his report. He said, these fringes were the joint effects of the portions of light passing on either side of the slip of card and inflected, or rather diffracted, into the shadow. So light that went around the left side of the card and light that went around the right side of the card, those light beams are bending into an area where they overlap. And when they overlap with each other, you're seeing an effect that is characteristic of wave behavior. Now, if it's characteristic of wave behavior, we ought to have some nice illustrations of it. My very favorite illustration of it is this photo that I found online, which is a picture of a bumblebee that has fallen into a puddle. And the bee is flapping its wings trying to get out of the water. And those wings are producing waves that go out in, expanding in semicircles, just like it would if you dropped a pebble into the ball. Now, there's a region behind the bee where something very interesting is happening, where those waves coming from the left wing and the waves coming from the right wing are overlapping with each other. And when that happens, you have this phenomenon that's called interference. This has to do with how the waves arrive relative to one another. So there are some regions where the waves from one wing overlap with the waves from the other wing, such that the peaks of the one fall on top of the peaks of the other. In those places, you get a phenomenon that's called constructive interference, and those waves add together to make a much, much bigger wave. Next to those regions, though, there are regions where the peaks of one wave fall into the valleys of the other, and they sort of cancel each other out. You get regions of relatively flat water where you don't see any waves at all. That's called destructive interference. And this alternation of constructive and destructive interference is characteristic of waves, and that's what Young was seeing in his experiments, and that's hopefully what you saw in your experiments. Now, this is a physics class, or a physics module in a science class, so there's got to be a little bit of technical terminology here. So I want to give you just a couple of things about the basics of waves that are important for understanding this. So if we were to write down a mathematical description of a wave, it would look something like this. It's a sinusoidal function, so it's something that's oscillating back and forth. And it's described by three key parameters. There's an amplitude, that is, sort of loosely speaking, how strong is the wave when it starts? What's the strongest it can be? There is a wavelength associated with it, and that is the distance. If you took a snapshot at a single instant of time, it's the distance from one peak to the next peak, or one valley to the next valley. And then there's also the frequency of the wave, which is if you sat at one point and watched the wave go by, how many peaks or how many valleys pass you per second, right? So we have an amplitude, that's the size of whatever is waving. We have a wavelength, which is the distance between peaks of the wave. And we have a frequency, that is the number of waves that pass per second. The key relationship between these that you also need to know is that the speed of the wave is equal to the wavelength multiplied by the frequency, right? And that means there's a simple relationship between these things. If you know two of them, then you know the third. And this is great when it comes to light, because we know that the speed of light is always the same, for everybody. That's a whole other area of physics that comes out of special relativity. There's a whole other courses about that. We'll talk about that some other time. The critical thing to know is the speed of light is always the same. The speed of light waves are always the same. So if you know the wavelength of light, you can very easily convert that to the frequency of light and vice versa. So there's this nice relationship between the two, and physicists will sort of move back and forth between them, depending on whether it's more convenient to talk about measuring the wavelength of something or talk about measuring the frequency of something. So this is our description of waves. How does this help us understand what's going on in Young's experiment and your experiment in terms of this interference phenomenon? Well, if we look at the waves passing around the object, we can think of this as waves coming from two different sources. Another way to get this would be to take a barrier and put two very small slits in it and let light pass through those two slits. And what you see is there is a pattern where these waves coming from the left slit and the waves coming from the right slit arrive either in phase, so the peaks are on top of the peaks, or out of phase, so the peaks are on top of the valleys, depending on how far you are away from the center of the pattern. Right? And this depends on how much distance the wave has to cover. So right in the center, the waves from the left slit and the waves from the right slit travel exactly the same distance, and they're guaranteed to arrive so that the peaks of one are on top of the peaks of the other. However, if you move out a little ways, you get to a region where the waves from the left slit have traveled less far than the waves from the right slit, and when they come together, the peaks of one wave fall into the valleys of the other. That happens because the waves from the right slit have traveled a little extra distance, and that extra distance happens to be exactly half of the wavelength. Right. Now, if you go a little farther away from the center of the pattern, again, the waves from the left slit have traveled less distance than the waves from the right slit, but now the difference in distance is one full wavelength. And if you've moved one full wavelength, that means that the peaks of the one wave and the peaks of the other wave are falling on top of each other again. And you have a bright spot. You have constructive interference. You see a bright spot in the pattern. This is the physics of the double slit experiment. This is the thing that Young is talking about in his report on this. And this is the essential physics that you've seen. Now we can do a little bit of geometry and see exactly what we expect to work out here. What you find is that if you do a little bit of drawing some triangles, you can show that the extra distance that one traveled is very simply related to the angle that you are away from the center of the pattern. And that extra distance here, if you look at this right triangle, you remember back to whenever you're doing trigonometry in school and SOHCAHTOA and all that, that's going to give you a pattern that looks like the sine of that angle. And in fact, that's exactly what we see. We see a pattern of bright and dark spots, and you get a bright spot whenever that extra distance that the right-hand wave has traveled is equal to an integer multiple of the wavelength. So you get this pattern of repeating bright and dark spots as you go out. So what you should see is that you have a pattern where you have lots of bright and dark spots, and the spacing between them is going to depend on the wavelength. So red light that has a relatively long wavelength is going to have its bright and dark spots spaced by a larger distance than green light, which has a slightly shorter wavelength, or blue light, which has a very short wavelength. So you can see that here in these pictures of the results from our simple experiment using the 3 different colors of laser pointer that I happen to have, because I'm a great big nerd and I collect these things. Now, what else is going on here? Well, we also asked you to look at light passing through only a single slit, and you should have seen a very similar pattern. You make a razor blade cut in a piece of paper and pass light through it, you see on the far side of it a pattern of multiple bright and dark spots that looks just like one of these diffraction patterns. What's going on here? Well, to understand this, we need to go back to Christian Huygens' original idea about the wave, where each point in the path of the wave becomes a source of new waves. Right? This gives us a way to understand why even a single opening gives you a diffraction pattern. Right? I can take that opening and I can divide it into pieces. I can think about a wave that's being emitted by the light right at the top edge of the slit, and the material that's light that's being emitted at the point halfway between. And what I find is that there will be a point where the light from halfway, right in the middle of the slit, and the light that's coming from right at the top of the slit travel different distances such that the difference is half a wavelength. When that happens, those waves are going to arrive out of phase with each other, and they're going to cancel out, give you a dark spot some distance out. And the position of that dark spot is going to depend on the wavelength of the light, and you're going to get the same sort of repeating pattern that we see from a double slit, but this time out of only a single opening. Now this cancellation is total because if the stuff right at the very top and right at the midpoint are perfectly out of phase with each other. If you move down one tiny infinitesimal increment to the waves emitted by the bit just below the bit below the top, and add those to the waves that are coming from the bit just below the midpoint, you see that exactly the same thing is going to happen. They're going to be perfectly out of phase, and it will cancel all across. So you get these dark spots all the way through the pattern. And you get the single slit pattern that has dark spots, even though it's only going through a single opening. You're not obviously splitting the waves onto two different paths. But you're still producing a interference pattern because you can subdivide the single slit. So if you compare a single slit pattern to a double slit pattern, here's some images from doing this very cleanly with professionally made scientific quality slits in the apparatus. What you see is that the single slit pattern has sort of wider maxima, where the double slit pattern you have much more frequent smaller bright and dark spots. In fact, if you look at this, you can see the double slit pattern sort of looks like a very rapid alternation between bright and dark spots, superimposed on top of a much wider one that is the single slit pattern. So in fact, what you see when you pass light through two real physical slits is a combination of the single slit pattern and the double slit pattern. We also asked you to look at a third situation, which is to poke a pinhole in a piece of paper and look at the light passing through it. In that case, what you should see is a set of rings. The argument for how this works is very similar to the argument for the single slit. It just needs a bunch more math. But the idea is you can think about there is at any given point, you can think of the whole circular hole as made up of concentric rings that are all emitting light in phase with each other, and there'll be places where all of those waves add up in a way that cancels out. So you get this nice ring pattern like you see in the image over here. We didn't ask you to do this last thing, but just for symmetry and because the history is kind of fun, I'll talk about one last phenomenon. And this goes back to a bit of the history. So Huygens put forth this wave theory. Thomas Young picked it up in about 1800, did his interference and diffraction experiments, which created quite a sensation and convinced a lot of people that the wave theory was for real. The French Academy of Sciences was at that time running a contest for who could do the best presentation of a theory of the nature of light. And a young engineer named Augustin Jean Fresnel submitted an outstanding presentation of a wave theory of light. However, not everybody was sold on the wave theory, including one of the judges for the competition, the distinguished French physicist Simeon Denis Poisson, who looked at the theory, didn't like it, and found what he thought was an insurmountable objection. He found a flaw in the theory. And what he said is, from this theory, you would say that if you took a round object and put it in a beam of light so that it casts a shadow, this same argument about waves adding up in a way that is in phase and gives you constructive interference, that argument would say that you should see a small bright spot of light right in the center of the shadow of a circular object. Poisson felt that was completely ridiculous. Nobody ever sees that. And he felt that conclusively disproved Fresnel's theory. Another of the judges, though, wasn't sold on that. And this was Francois Arago, who was later went on to become Prime Minister of France, an interesting career. He was an outstanding experimental physicist. And so he went to look and see if he could actually produce that. And in fact, you can. It's a kind of tricky experiment to do, But if you do this very well and line it up very carefully, you can find what is now frequently called the spot of Arago in the center of the shadow of a round object. So the image you see here is the shadow of a round-headed pin. And this is really nice because you see two different kinds of things happening here. In the lower part of the image, you see some bright and dark stripes. That is just ordinary diffraction off the shaft of the round-headed pin. And then you see a dark shadow from the head of the pin that's round. And right in the center of that, you see a small bright spot. That is the spot of Arago. That is the thing that Poisson had thought was impossible. That was an insurmountable objection to the wave nature of light. Once Arago demonstrated that this could be done and that you can, in fact, find a bright spot in the center of a dark shadow, that finally convinced the last holdouts that light is, in fact, a wave. And from about 1810, 1812 on, physicists the world over knew that the question of what is the nature of light was settled and that light behaved like a wave. Except eventually people came around to thinking that it's a particle again. And in the next video, we'll set up why it is that people started to think of light as in terms of particles again, and what the experiment is that finally convinced people that you really have to take the idea that light is a particle seriously again, despite the evidence that light is actually a wave. And so it actually turns out to be both of those things at one time. And that's the origin of quantum mechanics, and that's why quantum mechanics is so weird. But that's a topic for the next video in the series. So there'll be a couple of questions about this one for you to answer on Nexus, and then you can move on to the next thing, and we will talk about why everything I just said is not wrong, but not entirely correct. So we'll see you then.